Um, let's reassemble, set down those Bloody Marys, and let's return to talking about heat pumps. I had mentioned the H2No book that Andy Ask, who's actually sitting in the front row here, as the author of. Some really refreshing plain language about how mechanical systems can or should work. And so I think it makes it accessible to many people based on his a lot of years of experience, particularly dealing with high humidity problems in Florida, Houston, southern climes in particular, although his roots are in the northern climes. So we ended on a chart that said when heat pumps try and lift temperature a lot, their efficiency goes down. And one of the things that Bruce Harley asked is, how can you get a COP of less than 1? How can you put in 1 watt of electricity and get less than 1 watt of heat out? Actually, it depends a bit on the system, but a lot of the systems have their compressor outdoors, you know, the standard system. And as they try harder and harder to move heat, they get hotter and hotter. And they begin to lose heat to the outdoors. So if you're trying to heat the building and the compressor is outdoors, you lose the heat that you put into the compressor motor. And in fact, that's often how they fail. If you ask them to lift too much and run them all the time, they will trip out at high temperature. Because they'll get to 160 degrees, 180 degrees, you'll actually melt the windings, the insulation of the windings, and that's how they die. Otherwise, they'll just keep running, right? No matter you put them in Antarctica, they'll keep running. So they have to be protected from trying because they'll heat up, but their efficiency can be less than 1. Okay, so here is your standard outdoor coil that rejects or collects heat. In air conditioning mode, that coil on the left side of that Lennox unit warms up, warmer than the outdoor air, and then it rejects heat to the outdoor air and you cool the building inside. In heat pump mode, it will be colder than the outdoor air, and so heat will flow from the cold air to the relatively colder coil, and that heat then is pulled in and shed into the building to heat it. Now, the compressor that is needed to pump heat back and forth is in most North American systems inside that unit right there. And the reason it's shaped that way is that the compressor is, you don't want to look at it, it's like an ugly black thing. So you cover it with beautiful fins, right? And look at it, gorgeous, right? And so on the right-hand side, you see a slab, which is the other most common system, where you have a coil and a fan, you can see. And to the right of that coil and fan in that unit, you have the compressor, again, hidden from view by some attractive sheet metal. Those are the two most common systems. If you were interested in making a heat pump that was dedicated to heating mode, not cooling, you would put the compressor in the house. Because then you'd take advantage of the heat that's created by that compressor. And so you'd have to buy a unit like that from like Japan or Sweden or Denmark or Germany or Italy or China or, well, everywhere but Canada and the United States. And so the ones that are devoted to heating only, they actually take the compressor, put it indoors. And the first thing people go, oh, compressor indoors? Did I remember that you actually have a compressor in your fridge and in your freezer? You already have compressors in your house, and we use them all the time. It's not that odd to put one in your house. It's just not, quote, normal. But it is actually, wow, that was freaky. It is actually, oh, we have to do that presenter thingy. It is actually the ideal solution. So I know there's a manufacturer in Ontario who's working on a cold climate heat pump model, and they're putting all their compressors on the indoors, and it makes a significant difference under heating mode. Under air conditioning mode, of course, it's less effective, but if you have more heating to worry about than cooling, then it would make sense to do it that way. If you're in Houston, you're going to put the compressor outdoor because you're mostly cooling rather than heating. Pretty straightforward stuff. But anyways, we just haven't had a lot of options available to us. Okay, so cooling is clearly when we use this type of equipment, either one of these, and we pump the heat out of the house. The challenge is that with a single speed unit, it's pretty hard in any building, let alone a low load building, to make sure that you have a single speed that works for both heating and cooling and it's the same speed. I mean, it seems kind of stupid, right? But that is how most of our equipment works. Single speed, it's always on or it's always off, and there are significant performance implications by that. You just don't have good performance. You can't get the best performance. So in heating mode, the challenge is that the lift is much larger. In air conditioning mode, the return air temperature might be 75. The outdoor temperature might be 95 or 100, maybe 105 at extreme. That's only 25 or 30 degrees. In heating mode, the return temperature might be 70 degrees, but the outdoor temperature could be 0. That's a 70-degree lift. So it's at least twice as hard to get heat from 0 degree outdoors as it is to reject heat to an outdoors at 105. And that makes the equipment slightly different, and it makes it less efficient in heating mode. So in the good old days, we started heat pumps the first time around in the 70s in any sort of serious way. The heat pumps were basically accepted that you weren't going to be able to heat the house when the air temperature was below about 35 or 40 degrees, right? They just said, look, we're just not going to be able to get enough capacity for the crappy houses we're building that needed 50,000 BTUs an hour with the technology they had at an outdoor temperature of 40 degrees. So they would supplement the heating with electric strip heat, right? Everyone knows that. And so when the temperature dropped below X, what they call the balance point when you're in the heat pump business, the electric strip heat would kick in. Now what's interesting is that it doesn't just like add to the heat pump output. No, it shuts the heat pump off and you go 100% electric. And so, well, part of the reason for that is that, well, it's a heat pump. It's a single speed. If I add electric heat, I can have overcapacity. And so rather than doing that, they would switch to single, just turn it all on. Now, since that time, they've gotten a lot smarter about it, and they will have staged strip heat, so like 1, 2, or 3 stages. And you can often run the heat pump and 1 or 2 stages. And each stage would be a toaster or 2. I size things by toasters. They measure stuff by kilowatts. But your typical toaster is 1.5 kilowatts, and you can get strip heat in sizes of 1.5, 3, 4.5, 6, 9, things like that. So these are big electric strip heats. The other advantage was that they said, hey, look, if your compressor fails, at least you have heat. And you can just use your toaster. The disadvantage, of course, is that you had to design for really big copper wires and electrical circuits to run this stuff, because running a 9-kilowatt electric heater is something serious. And you needed to size the ductwork to handle the temperature rise that could be created by your 9 kilowatts. So heat pumps were a little bit annoying. They had big ducts, and often in practice in the early days, they spent a lot of time either accidentally or by manufacturer intent running with electric heat as a major proportion of what they did. And so when you looked at actual monitored programs from the late 70s and early 80s as they started to measure how heat pumps were working, they would find COPs of like 1.2. So 20% better than just the toaster. But of course, it's hard to even know if the COP of 1.2 was correct, because in many cases people were putting ducts in attics, in which case they were losing 20% of the heat they produced through leaks in the attic anyway, or the crawl space. And so actually you would have been better off with an electric baseboard, or even better off with an electric heating blanket. And so the energy paybacks were horrible. But from that time forward, things have gotten a lot better. Refrigerants have changed twice. Technology of the compressors is better. Controls is better. Sometimes some manufacturers have actually looked at heating seriously and tried to provide it. And the capacity needed in a heat pump is much less than it used to be as well. As we said, if I'm in Kentucky, I can easily build a 20,000 BTU an hour house for heating demand, and it doesn't take much of a heat pump to deliver 20,000 BTUs an hour. Whereas trying to go to Duluth, Michigan, or something like that, you're going to have a heating load, even in a good house, of 40, 50,000 BTUs at a design temperature of -10. Heat pumps still can't quite get there, although we're on the verge. But places like Kentucky and South, it's a no-brainer, or even Seattle and Washington State. So here's another one of my simple and easy to understand graphs, which shows how one would normally look at a single-speed, off-the-shelf, Carrier train, Goodman, Lennox, Rheem, whatever, heat pump. And the temperature outdoors is in degrees Celsius, so 20 degrees, 68 Fahrenheit. The assumption is that heating begins at 65 degrees Fahrenheit and increases linearly from there. That's what the line on the left, sloping upwards, says is heating load. As it gets colder, you have to provide more heating. Completely commonsensical, right? The reality of heat pump equipment is the heating capacity line that slopes upward on the left-hand side, labeled heating capacity. And when it is not very cold outside, it has lots of capacity because the temperature lift is small. As it gets colder and colder, the temperature lift gets larger, it has to pump harder, and so its capacity drops. Now, the normal rating temperature for heat pumps is, when they say that you buy a 3-ton heat pump, what outdoor temperature is that rated at? 47 degrees, which is about the temperature where a low-load house will begin to need heat. Not at all relevant to what is the heating, right? Because you realize that that may have made sense in, I don't know, 1972, but it doesn't have that much relevance to cold climates today. It still works in Houston because, you know, they don't spend that many hours below 47 degrees. It doesn't work so good in Boise, Idaho. What does? And so when it gets really cold, 47 degrees doesn't make much sense. But the rating point is 100%. Will be typically is going to be closer to this what they're showing rated there at about 10 degrees, a little less, between 5 and 10 degrees Celsius. Your capacity at 0 degrees Fahrenheit on today's heat pump will be about 1/3 as it is at the rating condition. So if you need 12,000 BTUs an hour at 0 degrees Fahrenheit, a rule of thumb is buy a 3-ton heat pump, 36,000 BTUs an hour. So if you need 24,000 BTUs an hour, then you need to buy a 6-ton heat pump. Because the capacity at around 0 is 1/3 of what it is at the rating temperature. That's a big deal, right? Now, so the other challenge is this. I have a low-load house. I need to start heating the house when the outdoor temperature drops to around 50. And now I don't need much heat, right, at 45, but I got myself a 6-ton heat pump. So when it turns on, man, I get heat real quick. And the problem, of course, is that the efficiencies under startup of all air conditioning and heat pump technology is low in the first few minutes and reaches a rated level after 5 minutes or something like that. And so if you run it for 5 minutes, your COP is much worse than rated, and you end up with these massive swings in temperature. However, as the temperature gets down to, say, 20 degrees, all right, now you're running your heat pump 35, 45 minutes on the hour, it's all good. And when you get down to 0, it's running flat out and providing all the heat you need. But for most of the hours you're talking about here, it won't work well. And so that's another reason why they often put in electric strip heating, is that you size the heat pump for some arbitrary temperature, maybe it's 25 degrees, and then any heat demand below that, you add electric heat, because otherwise it's oversized at 45 degrees. So the technology problems with heat pumps is not, air source heat pumps to be clear, is not that we can't extract the heat out of 0 degree air or even minus 10 degree air, because there are York heat pumps that are rated down to minus 10. But it's that at higher than rated temperatures, they produce way too much performance. And this is back to the limitations of single speed technology. So you need to come up with a way to change the output in relationship to the need. Well, let's just say, though, you don't live in a crazy cold place and designed for 0 degrees. Still not working? Yeah. Wasn't my fault, only me. Let's say I live in a zone 3 or 4. I think places like Seattle are classic because electricity there is of a low cost and relatively green because they have the Columbia River and all that good stuff. So you could buy a heat pump that would actually, in heating mode, be not far off of the rating temperature because a cold day in Seattle will be 30 degrees. It'll spend a lot of the winter season in the 35 to 45 degree range. And so actually, you can buy a 2-ton heat pump and it'll deliver 24,000 BTUs an hour, which is about right for a low load house. And when it gets really cold and your demand grows to 20,000, you maybe want to supplement with electric, but maybe not. But you can easily buy an off-the-shelf, low-cost system. So here I'm showing a 2-ton heat pump produces 16,000 BTUs an hour at 20 degrees Fahrenheit. So at 20 degrees Fahrenheit, I've already left Seattle. I'm going towards colder than Portland design temperature. And I can easily heat a low-load house with a 2-ton heat pump. Why 2 tons? Because that's the lowest cost-efficient heat pump I can buy as a commodity. But if I now take that same heat pump product and I move it to Boston, it would only deliver not 16,000 BTUs an hour at 20. When I'm down at design temperature of 5, it would produce 11,500 BTUs an hour. So, okay, but then it'll overheat me a little bit when I'm at 40 degrees. Make sense? Now the other chart, and by the way, it's actually, many of the manufacturers now have this type of data that you can look up, just get their engineering manuals, and it's all free download. You don't need any special connections other than the internet. You can see that at 20 degrees outdoor, we have a COP of 2.9. It's pretty good for Seattle. And if they're spending a lot of their time at 35 degrees outdoor temperatures, the COP is 3.7. That's actually really good. It means you're getting 3.7 units of heat for 1 unit of electricity. And that includes everything, right? It's a packaged unit, fan, compressor, everything. Not a bad solution. If I go to Boston and use this, it's a 5-degree design temperature. I only get 11,500 BTUs an hour, which might be fine for a really small or really efficient house, but not for your house. And now the COP is down to 2.27. So you see the efficiency is dropping as well as the capacity. So it doesn't work that well at these really cold temperatures. That said, we've used, in fact, this particular model and this particular unit, used it in San Francisco, and we've used it in Michigan, and we've used it in Waterloo. But you have to have a strategy of managing these large swings in temperature at higher temperatures, or supplemental heat in the form of hydro air or strip heat. So when would I want to use a heat pump like this with a supplement with strip heat in a cold climate? Anyone think of why I'd want a heat pump like this and then have to add electric baseboard or something to top it up with electricity at a COP of 1 when it gets really cold? If I don't have gas at the site, and I have an all-electric solution I need to use, this is not a bad combination, even in places as cold as southern Michigan, because I can put in an additional 1.5 to 3 kilowatt reasonable size strip heater, and now I have an all-electric solution. My seasonal over the year COP is lower, but it's still not bad. It still turns out to be in the mid-2s. And this equipment I can buy for less than the tax credit I'll get for buying a ground source heat pump. But so maybe, $3,000 I can buy air handler, outdoor heat pump, and 3 kilowatts of strip heat for this particular product. If I'm in San Francisco, just throw away the strip heat and this completely works. And even in Seattle, it'll probably work. And so those are the kinds of low cost, relatively high performance. But they're not great performance, they're just better than most types of performance. But you have to size carefully not to overheat when the outdoor weather is 40 degrees or 45 degrees. That's what you have to check for. Under 40 to 50 degree conditions, when you want to heat, how much overcapacity is this system? And you don't want it to be more than about 2 to 3 times overcapacity to avoid wide temperature swings. Okay, so how could I fix this problem? Well, the obvious thing is don't use a single-speed air conditioning system as a heat pump. Use a 2-speed or a variable speed. Now here the variable speed, unlike in the furnace market, really can make a difference, because I can now say when it is cold outside, 20, 10, 0, I can run either the high speed stage or run the compressor as fast as possible. And when it's 45 outside, either run the low stage or run it slower. And that way I can match my rising demand for heat with my diminishing capacity to deliver it. Change the speed. Does that make sense? So the trick is, what is the ratio between high and low speed? Well, here's an Infinity, what they call it, green something plus, with the Infinity Plus system from Carrier. It's a variable output. It gives me between 10 and 15,000 BTUs an hour at outdoor temperatures of 0 degrees Fahrenheit. And yet, at a temperature of 50, it only gives me 15,000. So that's actually tolerable, and that is not a huge range. And I can run it when it's 50 degrees outside. I only have to run it at 10 or 20 minutes an hour. And when it is 0 degrees outdoors, I run it at 60 minutes on the hour. So these things start to get to reasonable performance. The COP is still somewhat limited, but you will be getting, if I were to look at, say, the Waterloo, Ontario climate, let's pretend I have, on an hour-by-hour basis for a low-load house that this heat pump could heat, my seasonal, over the whole winter heating season, I get a COP of 2.9, something like that. But this unit doesn't cost me $3,000, it costs me $6,000, plus install, right? These are material plus install. So, yeah, you know, it works, but it's more expensive. But it's an all-electric solution. So if you're on a net zero energy house, or you want to do, don't want to do conversions from gas to electrical energy, you can buy one of these. Okay. Any questions about those basic systems? One of the things I wanted to add is that I sort of hinted already. When you're using a heat pump, as it gets colder, it's producing less heat, right? But the fan speed remains the same on the air handler. So as it gets colder outdoors, the air coming out of your duct is colder, which is not what you would like. You'd like really the opposite, wouldn't you? So that becomes a challenge, is that when these things are really being pushed low or wide range, you can easily be blowing 95-degree air on people. And there's all kinds of complaints come out because of that. And so again, you have to size the fan flow for that design temperature and manage where the air registers are located to avoid these complaints. And even then, you're going to need bigger ducts because the air temperature is going to be cooler than most systems. Did you have a comment? Well, I'm going to get to ground source in a bit. And I'm talking about air-to-air because I'm sort of working my way up from standard technology to WACO technology. So, and ground source is you know, much closer to standard than WACO, but so it's coming up shortly. I know you're waiting for the WACO. That's your kind of stuff, I know, yeah. So as we move towards WACO, one of the emerging technologies that's become fairly accepted, I think, to most people around, like ductless mini splits, you see it being used for air conditioning and point sources. One of the defining features of these ductless mini splits is that they're actually variable capacity. The compressor has variable capacity, and the refrigerant flow has variable capacity. So they're variable refrigerant volume systems with compressors that vary, in most cases, variably. Oh, they're definitely, it's possible to buy, but almost all stuff that doesn't have that, but almost all of it is. All the stuff that has any decent rating number is variable. So outdoor unit, almost always a slab system, not the canister system that is more common in North America. And the indoor units, originally, almost all we could get in North America was these wall warts, which basically you had to put on the wall and accept that that was the decor. And that actually is still the largest selection that we have available, and it is almost always, if not always, the most efficient model at the lowest cost you can buy. And you match that indoor unit to that outdoor unit, you buy that package. You can buy decent ones for like $1,500 and even lower wholesale price. But regularly you can get like units that have SEER ratings of 20 to 25 for $1,500 to $2,000. And the technology, not really does it just keep improving, it's more that they keep letting us have more of what they already have. So it's not like they don't have fancy, cool systems in Sweden, Denmark, Germany, Japan. It's that they don't sell them here because, again, it's like, well, nobody wants to buy them. Well, how do you know? You don't sell them. Oh, okay, maybe we'll try that. And then suddenly people buy them. The interesting thing about mini splits is that because they're actually much more constraining. When I buy this system, I buy an outdoor unit and I have a whole range of indoor units I can choose to buy. And then I can buy that unit in 2 tons, 3 tons, 4 tons, and 5 tons. These mini splits are bewildering to North Americans because it's like, well, first of all, you can't mix and match very readily across the line of a single manufacturer. And it would be impossible to hook an outdoor unit from Mitsubishi to Samsung. Whereas it's not at all unreasonable to try and hook an outdoor unit from Carrier to an indoor unit from Trane. And so part of the challenge is that these are kind of match systems, and navigating your way through which possible combinations are acceptable is challenging. And then to find out what the performance of any individual combination is even more challenging. And it helps when they start giving them labels like AUS9 RLS2 combined with an RTP-PUF. It's like, oh yeah, I'll remember that one. Yeah, right off the top of my head, right? So, you know, and that is not a real technical challenge, but it has been an adoption challenge, having people understand these things. Because they are matched, though, they do tend to be able to get some pretty good performance out of the box. And it's harder to screw up the installation, a little bit harder than normal split systems. This is work by John Winkler at National Renewable Energy Labs in Golden, Colorado, where they had the audacity to actually measure the performance of a commercially available ductless mini split across a range of temperatures. Frankly, I'd like to see some of this data for North American products, but anyway, this is measured for a Fujitsu 12 RLS. This is the coefficient of performance, and there's a whole bunch of dots here that show that if the temperature outdoors is 40 degrees, you can get COPs between 4.5 and 5.5, which I would suggest to you is pretty freaking good. So even in places like Seattle, which is not that cold, it's tempting to consider products like this because the COPs can be actually pretty high. And even as you get colder, the COPs under most hours of heating are going to be in the pushing 3 range, and occasionally they will definitely drop to 2 in the 100 hours when it's really cold or it's defrosting or something like that. But the measured performance that they report in both of these models they tested in the engineering manuals was very closely measured in the lab at NREL by a third party. This is the kind of stuff I wish I had for all of our equipment, is actual measured across the full range, compared to engineering data, so that we know that Fujitsu and Mitsubishi aren't screwing us. And in these 2 models at least, they aren't. Now, since that report was done on those products, the Fujitsu one has gotten better, and now the rated 12,000 BTU an hour model product on the left-hand side there, it's rated at 12,000 BTUs an hour. It's called a 12,000 BTU hour product. It produces 15,000 BTUs an hour of heat until the temperature drops down to about 20 degrees, and it's still producing 13,000 BTUs an hour at a little below, I think it's at minus 5 degrees Fahrenheit. So that's the kind of rating systems I like. Call it 12,000 BTUs an hour, and it works at least at that level or higher over its entire range. And that's what we've been seeing with a lot of these products, is that if you actually take the time to read the engineering manual, they tell you how they work. And they're not usually bullshitting. Like they're not playing that many ratings games. So I don't know, the HSPF, heating season performance factor, which is like an EER for the heating mode, didn't tell you about that, but they sometimes rate heat pumps that way, is about 11 for this. Its SEER value is 26.5, which is kind of like, I have a hard time understanding it could be that good. But at least in the heating mode, it seems to be working that well. And we've had some personal experience installing particularly this model, the RLS for a while, and then the RLS2, which is this enhanced low temperature range. Friends of ours in Nova Scotia who run an efficiency program have installed almost 700 of these and have some really good feedback about, what is the breakdown rates, installation screw-ups, and it's all been very positive, surprisingly. You put one in the downstairs, you put one on the upstairs, and you're done. Now, the bad news is that they cost like $1,600, $1,700. That's a bit of a joke, because that's not really bad news. The bad news is that they're different. And they have this ugly wall wart. It's like, why did you disfigure my house? Now, some of us can get over that. If you live in affordable housing or you care about the environment yourself, you might do that. But a lot of clients don't want to see that stuff. Oh yeah, here's the 9,000 BTU an hour model, which produces 16,000 BTUs an hour at 14 Fahrenheit. The input power under that column on the right is kilowatts, so it basically drags about 2 kilowatts and produces as much heat as it says on that table. And that's a 9,000 BTU an hour. That one's $1,475 or something like that. Last I checked, about 150 bucks cheaper. Now, the wall wart's an issue, and here's two issues with the wall wart. It looks like a wall wart is issue number one. Issue number two is all of the heat or cold is produced at that one spot. And so if I have my house or whatever, my apartment, will the heat or cold from that one location spread through the apartment? That's a really big question, active area of research in Building America right now to understand what are the potentials for these products. Now, one of the potential solutions is that you don't have to have a wall wart. You could have what's called a slim duct unit, which is basically a fan coil that doesn't do much air pressure, so it has to be a short duct run. Usually it's like 8 feet long of duct, and it just blows right into a grill. And so if you're making rich people's houses in China, you would use things like that. They would have grills high up, and they're quiet, and then the grill blows the cold or hot air in, and it sucks the air from a grill in another room, and so you move between two rooms, or you move from the hallway to the rooms, leaving all these units in the hallway so that you can access it without entering the bedroom, things like this. The problem is that most of these products, although it's slowly changing, as they release more and more to the North American market, don't have nearly the efficiency. They're such small units, they don't have very efficient fans, and so the efficiency really suffers. Now, it drops to like normal products. But there is hope that you can get these units, and we'd like to measure some to see there may be some real savings at part load conditions we don't know yet. And so we're hoping. Now, to mix air in a building with a single point of heat, we used to do that, right? If you think back, not you personally, but if you were to think about the history of 150 years ago, most people didn't have central heating systems. They would have like a fireplace or a pot-belly Benjamin stove, right? Franklin stove. And that one source of heat would have to spread through the house. And if you were to ask people who lived with those types, they'd say, oh yeah, it was really hot in the kitchen, and there'd be frost on the windows in the bedroom. But with a low-load house, the temperatures are not going to be anywhere near that extreme. But does that make sense? You know, as you get better and better skin, it doesn't take as much heat flow through the walls to equalize everything. The problem is that should be a solved problem, but except for that, people now have the expectation that temperatures are going to be very consistent through the building. So they have the house, the kitchen is at 72. If the bedroom's at 74, okay. If it's 70, maybe, but you know, like if it's 68. And so there are standards in the industry that say no room should be more than 5 degrees off of the thermostat. And a lot of times we're comparing these one point heat sources or cool sources and saying, can they meet that? And you were saying that in your house, the window shaker was a 7-degree temperature difference, which many people actually find quite okay, but it's not how the industry is, what their target is. Many houses don't have that. For better or for worse, they don't. But remember, we're in a world where you can buy a $30,000 car that has separate temperature controls for the passenger and the driver. And they're like readout in digital to the nearest half a degree, right? So that means that, people are going, what the heck? Like I just spent 800 grand on my house and I can't adjust the temperature in my bedroom on the top floor differently than the rec room in the basement? The short answer is mostly, you're right, you can. Sucks, I'm sorry. Now, it doesn't necessarily mean it's a big deal, but certainly as you move up market, people are looking for that. So one of the answers is, well, if you're up market, don't be so freaking cheap, buy 2 of them. One for the kitchen, one for the rec room, and one for the master bedroom. You can get units that are 6,000 BTU an hour rated peak capacity that'll throttle down to 2,000, 3,000 BTUs an hour. So if you have the money, that might be an option, but it's not a low-cost option. So we continue to look. Now, some of you who were at summer camp will remember Carter Scott, who built kind of almost production builder, zero-energy houses that aren't expensive, which that just seems all wrong to string those 3 concepts together. But somehow he's managed to do this. Well, one of the ingredients to his secret sauce is to use ductless mini splits for both his heating and his cooling. And he usually only uses 2 heads, one for the upstairs, one for the downstairs. And so we had an opportunity at BSC to measure some of the temperature variations across the walls and the rooms of these houses. So this is the East Hampton model. As you can see, it's a relatively simple shape, salt box model. Originally, they tried to not install air conditioning on the 2nd floor. And in the wintertime, it worked fine. They had a central heat source in the middle of the 1st floor, and the air would get hot, and it would rise, and cold air would fall, and we'll talk about that in a bit. So the hot air would rise, and so the temperatures in the upper floors were actually okay. But come the 1st summer, the reverse doesn't work. So they're blowing cold air around in the ground floor, and that didn't get to the 2nd floor, because of course the cold air wants to stay on the 1st floor. And so they install now air conditioning units on the 2nd floor in all their models to avoid any potential of comfort complaints. Okay, so Coda Bueno is here, someone in the back, like they're wearing the good BSC shirt, being the corporate man, henchman, as you say. And Daniel Burgi did this analysis and monitoring. The original results for unoccupied homes. They're still measuring these with people in them. But as you all know, as soon as you put people in houses, it screws everything up. So we obviously take pictures and start measurements with no humans around whatsoever to screw up the perfect palette that is our home. And then we're going to slowly add back people. But originally, no people. These are temperature plots. The vertical axis is the temperature in the bedroom or 1st floor, and the lower axis is the 2nd floor hallway. So we use the 2nd floor hallway as where the thermostat is. That's the baseline, and then we look at the temperature at the same time in the southwest bedroom, south bedroom, and 1st floor. This is actually wintertime, yes. And so under these conditions, up until about May, under these conditions, they're like within plus or minus 2 degrees most of the time. This is really good. These are really good results. No one should ever complain. And frankly, they build a lot of these and no one does complain. So yeah, well, first of all, there are no people in this house. Maybe that's why there were no complaints. And secondly, the doors were open. And by having the doors open, it seems pretty obvious to most people that you're going to get a lot of movement. And that's why the bedrooms are actually the place to measure, because they're the room that's most likely to have the door closed for the longest number of hours. And that's really the comfort point to look at. So Sometimes, this is now a probability distribution, there were a few hours, but not many, where we're as much as 3 degrees warmer. And actually, when that was tracked back and correlated with weather conditions, that was the southwest and south bedrooms when it was sunny and the solar heat gained through the windows. Now you'll notice, this is not a house that's known for excess of windows, right? It's quite modest, and they're triple glazed, low solar heat gain. And yet the excursions, the temperature excursions, are still driven by the solar gain. Now you start getting bigger windows, aiming for low, like high solar heat gain, and this is not going to work. There's no way that'll work with a central system, like a central hallway mounted thing. Now, before I show you some more results, or different results, I want you to look at the power draw here. This is the power draw for the heat pump as a function of temperature. Vertical axis is watts, averaged watts drawn to heat the house, and the bottom is the daily average temperature. So when it's 10 degrees outside, we're basically saying it costs 500 watts to heat the house. So I don't know, does this classify for the hair dryer award that people keep looking for? I don't know, but it doesn't take a lot to heat a house that's well insulated with a ductless heat pump system, even in the New England, Massachusetts climate. That's energy input. That's the key, because that's what I'm paying for. Surprisingly linear, although you're apparently ignoring all of the scatter plots. You know, like we can draw a straight line through any cloud. So here's another one, and this is from courtesy of Duncan Prahl at Ibicus. He's a 24 square foot high performance home in Philly described as passive house-ish. Is that right? Oh, sorry, was it Pittsburgh, not Philly? Oh. So this is a sunny day early in September. Remember I had told you about the challenges of Septembers and Octobers? Yeah. So this is a sunny day and it reaches near peak load, not just because of the outdoor temperature, because of the solar gain. This is a really well put together house by a lot of like committed researcher types who wear lab coats and stuff. And they bought a 2-ton air conditioner. Why? Because that's the smallest you can get that's any efficiency, even though they needed about 1 ton. And the result is that the temperature variations exceeded 5 degrees Fahrenheit from the thermostat set point. This doesn't mean that the house is necessarily uncomfortable, and I think, Duncan, you said this is a windmill you wanted to tilt at? The need for 5 Fahrenheit? I mean, I think it's just a completely reasonable question to ask is, you know, yeah, why is 5 degrees good enough and 5.5 not, and should it be 3? And yeah, for how long? How long can we deviate from set point? Because this is holding back the adoption by large-scale builders because they don't want to get into trouble to say that, well, you know, we had comfort complaints and we didn't meet the 5 degrees requirement. So there are, and some people probably want it more constant than others, right? So who knows? So here's the plots of solar radiation. The problem with Ibicus is they do everything in metrics so no one understands. And so it's watts per square meter. It's peaking at about 250 BTUs per hour per square foot of solar load at the top chart. Middle chart is outdoor temperature, just about at 90 degrees, somewhere around 5 o'clock in the evening, 4:30. And the bottom chart is temperatures inside various rooms. The red line is the temperature of the bedroom in the southwest. And the green, the purple line is the thermostat. And so we see temperatures there of deviating by almost 6 degrees Celsius, which is something like 9 degrees, 10 degrees Fahrenheit at the peak. And the peak temperature is getting into the 80-degree land in that southwest bedroom. And you know, it drops off later in the day, and by the evening it's back down to 76. And this is this is doors closed with just a basic undercut, nothing huge. Big, I didn't catch that. 4-inch undercut under the door so that nobody can be locked accidentally into their bedrooms. Pet friendly. That's a saloon door, man. That's no door. I'm not going to ask for the background behind that decision, But actually, so in other words, it's fairly connected relative to, yeah, yeah. Like I said, a researcher type house. Yeah. Now, I want to also say before we leave some of this heat pump stuff is that you can actually make like really big heat pumps. And if you leave the continent, I know it's a big deal, all that water and all that you have to get over. But if you leave the continent, you'll see that there's a lot of this stuff out there in mid-sized commercial particularly. Low to small scale to mid-sized commercial. On the upper left here is Enermodal's newest building, their headquarter building in Kitchener-Waterloo, Ontario. These are 20-ton, Richard, 20-ton? So that's 22 tons in 3 different units. And they're heat pump units. They provide the heating for the space and they provide the cooling for the space. And this is how many thousand square feet is this? This is a 22,000 square foot, 3-story office building with a very funky atrium. And the people who work there aren't very nice, but the building's very special. So this is a heat pump that will heat this building, even though the temperature you're designing for is in the 0-degree range or lower. And the building enclosure is, a lot about the standard stuff, but ICF construction, good windows, good air tightness, etc., etc. Fair number of windows, though. You're more than 40% a touch, aren't you? Just a little, 42, 43% window-to-wall ratio. So again, this is not a crazy amount of dollars to spend on a mechanical system for heating and cooling at 22,000 square foot, 3-story office building. Yeah, cheapest mechanical and simple too, right? Like in most ways, a simple system that can be installed by a single trade relatively straightforwardly. Separate ventilation system, which we're not going to get into. Now, and then over here we see Chris Schumacher and Koda Ueno sitting in a truck stop in New Zealand. And in this truck stop, you see those ceiling-mounted units. Those are ceiling fan coils that are connected to outdoor mini-splits, in essence. And this is a common way to heat and cool buildings in many parts of the world if you don't have access to natural gas or you're looking for an all-electric building. So these VRVs or VRFs, variable refrigerant volumes, variable refrigerant flow, are becoming quite a bit of an thing nowadays in light commercial as well. Although we're just, I'd say it's still early days in residential even with mini splits. Now, here's an interesting clash of the titans. This is a Goodman air handler unit being attached to a Daikin outdoor unit. Now, some of you who read the news may know that Daikin just bought Goodman 2 months ago or something like that for $3.8 billion. Apparently, they like the air handler. I don't know. So here we're trying to match those 2 types of technologies. The central air handler that North Americans are used to, you install it in the basement, attach it to ductwork, plumb it up to with flare fittings to a compressor, and the outdoor variable speed compressor from Daikin. The reason that I came across this was it was a 18,000 BTU an hour rated air conditioning system that actually was efficient and can run at 12,000 BTUs an hour. So because the indoor unit is a dumb unit, it's just a standard Goodman unit, it only works as a 2-speed system. So, but at least I can buy a 12,000 BTU an hour central air conditioning system that's not crazy expensive, that has very high efficiencies. And of course, becomes in a heat pump if you care, and it will produce more than 12,000 BTUs an hour at 0 degrees Fahrenheit as well by running the compressor at high speed to get that output. So this is to me, I thought this would be a pretty happy combination that would allow people to, use lower load air conditioner heat pump technology as a central system. I don't know if people just don't know about it yet. It's been on the market for at least 3 years, and it doesn't seem to be taking off for some reason. It seems like it has some pretty interesting crossover potential. I don't have to look at the unit. I can have the basic one in the basement. Okay, Any questions about that mini split stuff? Let's talk about chillers. Chillers is another one of those words that's like, why did you invent a word to confuse people? An air-to-water heat pump used for cooling water is called a chiller. That's all. Now, big buildings often have chillers, and they reject the heat to the air not with an outdoor condenser unit. They have a cooling tower and all kinds of crazy gizmos to get rid of the heat because it's big. But it's just taking cooling water and rejecting the heat to the air. That's what a chiller is. Now, we can get small chillers as well. An air-to-water heat pump that's available in 2 tons or 3 tons or 4 tons. And then they have things called reverse cycle chillers, which is, well, it's just an air-to-water heat pump working in heat pump mode. It's not, people go, oh, you hear about this reverse cycle chiller technology? No, but I can pretty much figure out what you mean by the words, and it is basically air-to-water heat pump. So let's take a look at some of the products out there. Multi-Aqua in the upper right-hand corner, Aqua products in the lower left. The Aqua products is interesting because what you do is you buy a standard unit from York or Carrier or Train, and you plunk it on top of this grayish-green box, and it takes the refrigerant and turns it into cold water or hot water, and the hot water line leads into the house. So basically, that's a way to get chilled water, and now you've got a hydronic system, right? So now you have an electric way of making hot and cold water, and therefore you can put it into a tank and separate out the load demand from the load production. Back like the combo unit with a tank. So now I can actually heat or cool a 2,000 BTU an hour apartment or a 28,000 BTU an hour house with the same product. Just the tank in between, either the pump runs often or not often. Now, one of the things about this is that if you make water outdoors with the outdoor unit, you'd probably have to worry a bit about freezing, huh? So this product tends to be mostly used in the southern states. You throw a little bit of glycol in the water, and that rare freezing snap doesn't do anything to you. But if you try and use this in Minneapolis or in Boise or whatever, you really have to do a serious job of insulating the water lines from outdoors and insulate the cabinet and use a lot of energy in antifreeze actions. So it runs to keep it kept warm and crazy stuff. Now, in Europe, there's a lot of these air-to-water heat pumps because they have a tradition of using hydronics to heat and cool their buildings. And so as they move to heat pump technology, because the technology is getting better, they have a lot of them. And Dimplex is one big company that from Germany that does these things. And the problem, here are some charts. Again, the good news is that they'll provide you some data. The problem here is that as you try and produce really hot water, your efficiency really drops off quickly. So if you're willing to live with water that's 105 degrees or 95 degrees, your efficiencies are on par with an air-to-air heat pump. As you start asking for warmer water than that, say you want 120 degree water, then the efficiency starts falling off. And the left bottom there is the COP as a function of outdoor temperature, minus 20 degrees Celsius, meaning 0 degrees Fahrenheit, roughly minus 4 Fahrenheit. If you produce water that is 95 degrees, you get a COP of 2. If you produce water that is about 130, 125 degrees, your COP drops to 1.5 at those temperatures. And capacity drops pretty quickly as well. That's the upper right-hand corner. It's the capacity in kilowatts. Multiplied by 3 point something to get BTUs. And again, the capacity drops off a lot as you get cold. So you have to buy oversized equipment if you're in a cold climate. And that just to meet the minimum load. How many people here have heard of Altherma? I'm assuming there'll be a number of you. So here is a North American product. Well, not really. It's sold in North America. I can buy a Korean product that they let us have. And this is an air-to-water. It sounds pretty cool, but when you dig in, it's not that great. First is, it heats only to about 130 degrees. And so if you want to use it for domestic hot water, you don't really get hot water, you just get 130-degree water, which is barely adequate. Why does it only heat to 130 degrees? Because it uses, if you'll notice on the brochure there, R410. And that's about as far as you're ever going to go with R410. You have to change to a different refrigerant to get hotter water, because the refrigerant will simply break down at higher pressures and temperatures. It's the curve of the enthalpy curve. So at outdoor temperatures of like 20 degrees, if you try and produce 130-degree water, your COP sucks. It's like 1.5, 1.6. And they're not very forthcoming about providing these full charts of data, so I'm piecing together various published tests. But the advantage is this. You have one product that produces hot water for space heating. The same product produces domestic hot water, and the same product can be used for cooling in the summertime. So you can actually, here's a chart of one of the installation methods for the Daikin Altherma, is that I have an outdoor unit, the refrigerant comes indoors, and therefore there it changes its heat into water. So you don't have any freeze problems. Okay, so that's smart. Now, that water could actually be used to heat the house or heat domestic hot water. And if you want to have an air conditioning mode, it can actually suck the heat out of a water tank that makes cold water for fan coils or floors, and takes that heat and puts it into domestic hot water. That should excite you. Wow, that's great. Now, the one trick that they're not yet doing, but wouldn't take much, is to then say, now I could cool air with a fan coil and cause dehumidification, and take the heat and put it back into the room to get reheat. That would now be free. So I could actually make it run in dehumidification mode. They haven't yet figured out that that anyone would care, but you could do that. Now, all of this can be yours for somewhere between $12,000 and $15,000, plus maybe a little bit more. Now we've been told by Daikin, at least in San Francisco, they're saying, oh, that's just because the installers are screwing you. It really shouldn't cost that much. I'm going, I agree it shouldn't cost that much, but that's what it's costing us, right? And so that is what they've basically positioned themselves in is between ground source heat pumps, there's this Altherma air to water, and then there's all the other stuff that does the same for less. And so there is a challenge in, now these guys I don't think get a tax credit because they're not called geothermal, which makes them immediately more expensive, right? But there's some other systems. You can get this type of a system from Fujitsu. You can get it from Mitsubishi. You can get it from, in this case, here's an LG. I thought they had the nicest drawings, so I showed you them next. But you can't buy any of them here. So they're all low load capacity. They're variable output, so they can slow down the compressor when you don't need a lot of heat and speed it up when you really do. And they use water as a medium so you can store it and make both domestic hot water, space heat, and space cool. So we're getting closer to the magic box. It's just that water is in the way. Yeah, all that water between us and them. Now, I'm going to get wackier yet before I get to CO2, before I get to ground source. Switch to CO2 as a refrigerant, and now we're like, very cool things can happen, or hot things, depending what you'd like. So it's easy to make hot water at temperatures over 140 degrees. The pressure required to do that is somewhere like double the R410 pressure. So if anyone plays around with air conditioning units and you see the pressure in your 410 rise to 600 psi, usually you'll get very worried. That would be kind of like normal operating pressure for CO2. And when you're trying to get to temperatures of hot water of 140, 145 degrees, 900 to 1,000 psi would be normal, which means that you got to have good seals and thick walls in your pipes and all that stuff. It also works rather well at temperatures down well below -10. Most of the products find no need to rate lower, but in the lab they can do this down to -40 and they still work because it's CO2. And again, you can't buy it here. So this is a Swedish house in the lower left, an outdoor CO2 unit. Notice it's standing up high on stilts so that the snow won't block it when the snow piles up. 4.5 kilowatt unit, which works out to a rated load of about 15,000 BTUs an hour, but it's variable capacity, so she can dial right back down to 4,000 BTUs, up to 15, 16,000 BTUs as needed. And the indoor unit is basically you attach your refrigerant lines to it. It has a tank and the controls and some pumps. And you attach to the hot water, or you attach to the radiators, you attach to fan coils, you attach to floors, and it all works. And the problem is that there is a desire, especially amongst engineers, to make a magic box. And as a consequence, we're often sacrificing performance by putting everything, heating, cooling, hot water, it slices, it dices, it makes julienne flies, and you put it into one product, you're going to lose something. But that said, people are looking for simpler solutions, and if they're complex but come in a factory-made box, it's not as bad. And I mean, Lloyd, we've talked about that too, about ground source heat pumps, is that if they come in a factory-made box, complexity isn't a big obstacle because they're going to make a 10,000 of them. It's as soon as you have to wire some of this stuff or pipe it in the field is when it becomes a complete freaking disaster. So we'll see. We don't have, this is blue sky stuff, right? This is wishing for the future, and we'll know when we have a dozen houses and a few years of experience. You didn't come here expecting answers, did you? No. God, a lot of answers. So, ground source heat pumps is actually simply a water-to-air or water-to-water heat pump, which uses as the outdoor sink and source is the ground. So you run a loop through the ground, sometimes a well in the ground. And so you extract heat when you need it from the ground, and you dump heat into the ground when you don't need it. Now, geothermal is actually what happens when, like, you know, Old Faithful, you know, the guys, you drill a hole in the ground and squirt steam at you. That's geothermal. When you're trying to get Mother Nature's energy bounty in Maine in January, and you're like down 6 feet, the water is there like it's 34 degrees. Right? And you run the heat pump for a while, and the return water temperatures get to 32 degrees. And they tend to peg there for a long time as the ground freezes around the pipe. So this is hardly a Mother Nature's bounty being given up to you because she loves you. It's more like clawing from Mother Nature's eager grip any last bit of heat she's willing to cough up. But the huge advantage, well, there's several, but one of them is that at least the ground loop is 32 degrees. We're not talking air temperatures of 0. We're talking ground temperatures of 32. So your temperature lift in cold climates is limited to about that, 32 to 37 degrees up to the temperature you're wanting to pump to. And that means you're always going to have a higher COP in the compressors than you are when you're pumping it from outdoor air, always. Now, unfortunately, I shouldn't say always, because by the time I get to March, the ground temperature is still 32, but the air temperature can often be 35 or 40, and then suddenly, actually, maybe the air source looks better. But over a season, you're going to do better with a ground source. The challenge is that you actually have to pump water through the loops, and the loops have to be fairly long to get the heat into or out of the ground. And if you're not careful with your pump design, your pumps can consume a lot of energy. This problem gets larger the smaller the heat pump. And so when you're talking about low load houses with, like, you know, a demand at 18,000 BTUs an hour peak, running 150 to 300 watts of pumping can really change the COP, and does. So when you actually include that into the calculation on low load houses, the COP doesn't look that great, unless you're really smart about it. Long loops with big pipes, slow moving flow, efficient pumps, very little friction in the things, then you get back to closer to the numbers. Now, how do they sell ground source heat pump equipment? Well, they use COP, right? And obviously bigger is better. The problem is that if you're just selling the heat pump, the water-to-water heat pump, the rating doesn't require that you include the pump energy that's required to move water through the ground, or the fan energy or the pump energy required to distribute it through the house. By excluding those two electrical loads, you see advertised COPs of like 5. And they're true. It really is true. It just has no relevance to how much energy you'll use when you build it into a house. And that's a common scenario, right? Absolutely accurate number with absolutely no relevance to what you're doing. Now, if there's another rating standard, if you buy a packaged heat pump unit with a fan and a pump, that will actually include the fan energy and the compressor. But what you really want to make sure is that you've got the ground loop pump, the compressor, and the fan or the pump in the house, and include all of them together. When we start seeing that, I think we're going to start getting better performance from ground source heat pumps. I was speaking to some of the people here, I have not seen third-party verified measured data of ground source heat pumps with a COP in the wintertime over 3. Yeah, although they're routinely advertising 4 or 5 and more. And the studies that are out there tend to show well-designed systems in cold climates get you 2.5 to 2.9. Okay, not horrible, but you'll notice that those ductless mini splits will get you the same thing. And all you need to do is remove a 0 off the price tag for the ground source heat pump. It's in that, literally in that order, right? We're at least 5x less and sometimes 10x less. Now, when it comes to low load houses, it's hard to justify spending the Altherma 12 to 15 grand or the ground source 20 grand before tax credits, before subsidy price, because it's just a low load house. Like, how can you justify spending that much money on HVAC for a low load house? And that's why we end up back to the simpler systems and thinking that maybe we can get away with that even if the efficiency isn't as high, Now, as you get to larger buildings, bigger pumps, bigger compressors, etc., when you are doing like a school and you have a low load school with a total heating demand of 80,000 BTUs an hour, a total cooling demand of 40, hey, a ground source heat pump can actually start converging on a good solution because there's a kind of large fixed cost to get started and do the engineering, and there's a relatively small incremental cost. And then once you get really big, it starts to not make sense anymore, and there's this good sweet spot, but it ain't in low load houses in my opinion. Yes, sir. Yeah, so the comment was I including the effect of the ground getting heated up and cooled down over the season? Kind of. So if you design the loop properly, the loop will barely hit 32. And if you're a little lucky, you can keep it at 35. But 32 is a pretty realistic low-end number at the end of the winter. And in the summertime, you don't want the temperature to get, in this colder climate, you don't want it to get over 70. But let's say I go to Houston, and the groundwater is already 65. It doesn't take long before the groundwater rises to, the return water temperature from that loop rises to 80 or 85, and very quickly your performance spirals to less than an air-based system, which is kind of shocking when you think about how much effort we just put into the system. Now, again, it comes down to design. It's not a fundamental flaw, and it's not even a common problem. It is an occasional problem. Oh yeah, I've heard of it too, absolutely. It's an occasional problem that in the south, they have heat-saturated loops, and you may as well just put an air source system in. And in the north, it's common that the pipe actually gets down to lower than 32 and can't actually meet capacity, so you add a boiler. In fact, in some cases, and I don't know if maybe Richard Lay even knows what I'm talking about, we had a case where the water came back so cold, heat pump couldn't keep up, person came back to fix it, installed a gas boiler. And so they would warm up the temperature of the water coming out of the ground so that the heat pump could run it, but the control system wasn't quite right, so they were basically shooting a whole bunch of hot water into the ground source heat pump, which stopped working, but a lot of heat did go back into the loop, and then eventually the heat pump started working after several months of the gas boiler heating up the ground to a warm enough temperature that the heat pump could work again. That was about the start of summer. And so, and then, so, you know, like, part of the challenge is that you got to design the ground loop right, and there's every incentive economically to make the loop as short as possible, whereas all technical things says, make it a long loop, make the pipes big, and you'll be safe. And none of this will happen. But that's not what people are trying to do. And so when we buy a split system from Goodman, or Carrier, or Bryant, or whatever, I mean, you got the heat exchanger, you know what the size is, both on the inside and the outside, so there's that part of it is harder to screw up. Not that it can't be, right? Difference between genius and stupidity is there's a limit to genius. Bruce. Cool. Right. So all the conversation we've been having about ground source has been closed loop, pipes that and go through the round. It is presumed in colder climates that an open loop where you pump water in one well and pull out another should give you more efficiency because the water should pass through more soil. And so it should come back warmer in the wintertime. And it does. Instead of 32, it comes back at 40. But the challenge is that the pumping energies to pump water in and out of those wells really starts to get nutso. And it's particularly nutso, not even the 5-ton systems, it's when you're doing 2-ton systems. It's when you're doing low-load buildings. That pumping energy just kills you. And according to ResNet and industry agreed upon terms, you don't even make it to a SEER 13 in cooling mode if you use default values. So now, can we fix some of this? Yes. We can get better pumps. We can get better heat exchangers. We can get better controls. The problem is what I'm describing is more than half of what's out there. And this is why I make fun of the tax credit, because it's like, really? This is what we're giving 6 to 10 grand a shot as a subsidy for? I mean, it just, like, without any real measured data, it just boggles my mind that this is going on. The technology's obviously got possibilities, but you can't just willy-nilly apply it and hope it works, which we have been. So you can buy small systems down to 1.5 or 2 tons. Some of them are variable speed because they have water tanks. You instantly have a low-capacity system, right? Run the ground source heat pump for half an hour, store the heat or cool in the tank for the rest of the day. And actually, if you start doing that, the loops can be getting really short. In a low-load house, you could get away with a 400-foot loop, which is basically twice around the house foundation during excavation, out to the front curb and back alongside the power line and the trenched-in cable line. And boom, already at 400 feet. So there are some builders who are able to do that kind of thing, is use the existing trenching, coordinate a simple 1 or 2 pair run at relatively low lengths, and then you use a small water furnace type heat pump system, water tank, and now you actually get some really low energy consumption, and it actually will handle loads that are very low, 2,000 to 30,000 BTUs an hour loads, all off of that 2-ton system. Still not cheap, but at least we're getting into the, if you're smart, you can get that down to 12,000 bucks or less, under 10 with tax credits. But it does require more careful design. I can't just say, buy product A and install it following manufacturer's installation instructions. It means you have to actually coordinate with the people who are digging holes in your job site. So if you're doing $250,000 houses, that's a real option. Now, Carter Scott had that option, but for him, ductless mini splits are just definitely cheaper, and they do the job, so he doesn't care. Now, de-superheaters. What is a de-superheater? It sounds like super sounds good, but D sounds bad. And heater's what I want, so I'm so confused. What is a de-superheater? So there is, in this refrigerant, when you compress it and then release it and expand it, you get a lot of energy when that refrigerant condenses. That's where most of the energy comes in. But there is some energy in the gas just cooling down before it condenses. And that's what a de-superheater does. It takes the hot gas and cools it down a bit before condensation and sucks out that heat energy, because that heat energy is at a high value. So a de-superheater can produce 140, 120 degree water relatively easily. So the idea is this, is that when you're running your ground source heat pump, you could take some of the, instead of cooling to the earth, you could take some of that heat out that's at a high value and put it into your water tank. And people have heard of de-superheaters, right? They're pretty common, yeah. I mean, I don't know if it's a third or a half of all these ground source systems have them installed right out of the box with them. The challenge is that the proportion of energy that you can extract at a high temperature relative to the total heat flow through the heat pump system is fixed. It's fixed by the physics of the refrigerant. And that means that if you're moving 12,000 BTUs an hour through the heat pump, you can, via the de-superheater, extract maybe 1,200 BTUs an hour. That's about the best that physics will let you do. Now, on a low-load house, what that means is, since you're not using it a lot, you won't get a lot of hot water. And again, many times, it's not worth the pumping energy for the amount of de-superheat you're going to get off of it. You know, it's a bit extreme, but on the low-end side. But it certainly is far from what the brochure says, which is free hot water. Free my ass. I mean, I spent $20,000, and you're going to tell me that I get 500 gallons of hot water a year for free? Well, yeah, okay, maybe. Oh, and I have to pay $1,200 as the option to be able to do that? This is far from free. But anyway, that's what the brochure says. And if you're building a big house with a lot of cooling demand, like say you're putting in a coupled 7-ton system, 2 7-ton ground source heat pumps, you're running them a lot in the summertime, you will get enough hot water to heat for 1 or 2 people. But if you have a small system, you're not going to produce enough hot water for a family by any stretch of the imagination. Oh, so the comment there was that you have to be careful that when you're running your air conditioner, you're not using hot water. Therefore, you can't take full advantage of it unless you get these storage tanks. And that's where the pump and the tank, that's where the dollars come in as an option. So you need to preheat the incoming cold water with de-superheat and then let it go into the actual heat, the electric hot water heater or something. You say 20%, yeah, that would be good. That would be a good day if you can get 20%. If you do it all right, you get 20%. And again, I go back to monitored studies. When people actually measure groups of houses installed according to the ground source heat pump associations who offer them up, they get numbers that are more in the 5 to 10% range, but it's always higher for big houses and smaller percentage for small houses. Yes, Andy? Yeah. And when, so Andy made 2 points. The one is that if you're running an air conditioner in Florida, an air or water source, and you run it for many hours of the day, that's when you get the value out of your de-superheater, because you get a constant trickle of hot water, put it in the tank, and that's good. The challenge is that because the city water coming in isn't perfectly clean, it eventually can clog up the de-superheater heat exchanger, and in your mind, before it ever pays for the de-superheater. But at least the technology exists, could work, but there's these real practical issues of coincident use, using it enough, etc. So it's not free. Okay, last thing before the break, electric resistance heat. Electric is cheap to buy the equipment, relatively speaking, but it has, in almost all jurisdictions, a high operating cost. Now, that doesn't mean it always costs the most money to operate. It's just that per BTU of heat, it tends to be the most expensive solution. But as we talked about on things like fixed charges with gas meters and stuff like that, if you're building a really low energy house in Bowling Green, Kentucky, and your annual energy use is $17 worth of natural gas, and your standby charges are $170, you really have to start asking whether or not $90 worth of electric heat isn't the better answer, right? Now, I still have a problem with it because electricity is a high-value energy source. It's the most polluting energy source we have in America in most places, so I'd like to avoid it. But if you actually get your loads that low, you know, you're allowed to just use straight-up electric. And then there's a number of ways to do that. Electric baseboard, which everyone loves because it's a high-value product. But you can also embed it in the floor. You can buy mats underneath the hardwood. You can embed it in the ceiling. You can embed it in plaster. You can buy panels that look decorator of various types. And so you can put it in a lot of places. And so someone wanted me to point out that heat doesn't really rise. That's why you can heat the ceiling. Hot air rises. And in fact, hot air doesn't even rise. There's no force pushing hot air up other than cold air falling. The force is when air gets cold, it shrinks and it gets more dense and it's pulled downward by gravity. That pushes less dense warm air up. So a little bit of cocktail conversation. Did you know that hot air doesn't really fall? It's actually cold air that falls and pushes the hot air up. So, and heat never rises. Right? If you take a piece of copper pipe, you heat the top, you're going to burn your hand. I mean, it seems obvious, but people are regularly confused by the distinction between fluid like water or air floating up because of the cold falling and thinking that that means I can't heat the ceiling. Baloney. Of course you can heat the ceiling. It's just because that's radiation, not airflow. If we're talking about typical low-load houses, you might end up with 300 to 600 watts of installed electric capacity in a medium-sized room. Typically, you want to worry about cold spots around windows and so on, and offset that with panels that are either above, below, right next to, etc., the window. There's even a product out there that they use the window as the electric heater, because low-E coatings are actually electrically conductive. So they said, hey, well, why don't I put a low-E coating on the inside and then just like juice it? And when they did, I love people like this, and when they did, it actually heated up and it actually warms up. And so you can actually get a window that warms up to like 15 degrees above ambient temperature in the room, and therefore it's the warmest surface in the room in the wintertime. Freaky, huh? Pardon? Well, it doesn't have that. It doesn't have a problem in that it has a good enough ground that it works, and they've basically apparently shown this works safely. Maybe you can't lick it. I don't know. Or pee on it. I know, Coda. Okay, can't pee on it either. You could also use microwaves to heat people directly. That's right. And then there's like the sweater crowd, right? You could wear a sweater or slippers. But anyway, so the challenge, of course, by heating the window directly is that you do increase heat loss through the window. And so I don't have a problem with heating the window as a source of heat. I have a problem with that you're losing some of it through the window. And so you're better off with a radiant ceiling panel above the window. And one of the advantages of radiant ceilings is that it's hard to cover them with furniture. Whereas radiant floors, not so easy all the time to keep the furniture off of them. But baseboards, etc., coves, you've seen the electric cove heaters, again, can't be obstructed by furniture. These are options, and they make sense whenever the load drops low enough that it doesn't justify capital and fixed charges for things like natural gas. Now, often it's not fair to look at natural gas and just talk about the heating cost, because we're using natural gas also for what? Domestic hot water. So that's a big one. And what else? Cooking. Not a large use, but we still use it. What's a bigger use than dryer? So in order of significance, in typical houses, it's natural gas is first used for space heating, then domestic hot water, then dryer. In a low-load house, it's going to be domestic hot water and space heating are going to be out the same, and dryer, if you're a normal American family, is only like a third of domestic hot water, a third to a quarter in that range. So it's not a trivial use. So if you were doing the analysis, you should say, is it worth getting the natural gas for hot water, clothes dryer, and space heat? And if it isn't, fine, then those go all electric, right? But you gotta do the fair comparison. It's not just the heating only comparison. Got to look at those other uses I said. These are all interactive. Now, just to go really quite, yeah. So the comment was that there has been a precipitous change in our generating mix in the last 3 years, and it really has been an unprecedented shift in reduction of coal-fired generating capacity and a switch to natural gas. If anybody had told the industry 5 years ago that it's a national emergency, I need you to drop coal-fired percentage of electricity from 50 to 38%, they would say, in-freaking possible. But as soon as the price changed, they all seem to manage to do it quite willingly. And so that means that our grid is getting cleaner. And it was and I don't have the new numbers. Maybe someone from NREL does, but they're definitely getting better. Well, the 10 to 15 watts per square foot was of the actual panel, not of square foot of house necessarily. That's right. No. I mean, it depends all over the place. You sell ceiling panels, so I know you believe that. But it just I just don't have that experience very often. And panelized systems. So if you want to do really carbon neutral, You can actually have a fireplace of wood that you grow on your property and cut with an axe. Then the axe has been made of recycled steel and burned by wood or something, right? So, but there's actually more practical options now, which are things like pellet stoves. And the reason they've become that's the picture on the lower left. That is somewhere around a 20,000 BTU an hour peak output pellet stove fireplace that looks like you could have a date in front of it. I mean, with the flames, it looks pretty nice. It also has an automatic control system that actually will throttle it up and down based like a thermostat, because the pellets can be fed in with a little auger a little bit at a time. And if it gets too hot, it just slows the auger down. Gets too cold, you pick up the speed of the auger. And the pellets, you basically have like a bag of dog food, and you open the lid up and you pour the pellets in, close the lid, and you're good for a few days. And so this is something where if you really want to do wood or some other biomass, corn, because it's so cheap these days, you could actually get like these pellet stoves that are automatically controlled and have low output. There's not many of them. The ones that look good and are low capacity are from, not surprisingly, Europe. This is the Rika, is the company from Austria that makes this one. And they actually, in some locations, and if you're, say, in Maine or New Hampshire, where there's like a lot of trees, and you basically have to cut them all down just so you can get anywhere, wood seems like a reasonable resource to use. Probably not such a sensible thing in Phoenix, where they have to import, ice cubes and wood and stuff like that. The one on the right-hand side is a slightly larger model that's sitting outside. It's 50,000 BTU an hour, but it sits in the parking garage or something like that and can be used to heat like a 10-unit apartment building and also make the domestic hot water. These types of combustion units, again, have no issues with producing high temperature, right? There's no efficiency loss to say I want 140 degrees. And so you immediately, no problem, go to 140 degrees, no efficiency loss to have those things work that way. Okay, just before a break, the dehumidification, as I've mentioned several times, cooling only will require supplemental dehumidification, and this requires a cold surface, like fan coils. The problem with radiant floors is that radiantly cooled floors, right? You could cool a ceiling or cool the floor, but you can't cool it below the dew point temperature of the air in the building. And it does zero dehumidification. You want it to do zero dehumidification. Yeah, sorry. Let me be clear. It's supposed to do no, and you don't want it to do any dehumidification because as soon as the water starts condensing, you're in serious caca. So you still, particularly with a radiantly cooled floor, you're going to need a separate ventilating dehumidification system, which is not an inexpensive system, and it's not easy to find. But you can do it, and for a very low load, zero energy office building, I do that in a heartbeat. Radiantly cooled ceilings, separate ventilating dehumidification system, you're great. But when you get to low load buildings, the equipment is just not available that's small, efficient, and affordable. And so you have to kludge something together, and for custom homes you can do it, usually not worth it. Just usually not worth it. Separate dehumidifier is a common requirement. As I said this morning, I'm not quite willing to say every low-load house has to have a dehumidifier if it's air conditioning, but I'm pretty close to saying that. Because I really think that if you're east of the Mississippi, it is going to be 90% of low-load houses are going to need to have a supplemental dehumidification of some type or tolerate higher humidities and higher temperatures, some combination of that. Multi-speed AC, and Andy, you can probably speak to this as well, but multi-speed AC air conditioning systems, the two-stage, so that they can run for long periods at lower capacity, seem to make a difference. And so that those few percentage of houses that you can normally get away with, maybe a quarter of our houses can get away with it. Or if you just build a little bit shittier, maybe 50% of your houses. And would you say it's something, okay, Andy, who has a lot of experience in Florida area, etc., is nodding here. And so the challenge is that if you don't really build a little bit crappy, even the multi-speed AC won't do it. And so, and it's all about the sizing. It's all about how many hours per day does that thing run in the the seasons in which humidity inside could be a problem. That's the real question you have to ask. And if you can answer that and say that, oh yeah, the system I'm installing is going to run several hours a day minimum when I need dehumidification, you're probably going to be all right. And if you can't answer that question with it's going to run several hours a day, then you need a supplemental dehumidifier. So, okay, let's have a break. I'm going to come back and talk about domestic hot water. Not the wild stuff, this is the domestic stuff.